So let's assume for a moment that we're working over some U, which is a model DCF0, which saturated over K, the field of definition of V. So V is over K. V is over K. Okay. Yeah. So a monster model.
Oh,
sure.
okay. That was
Fine.
okay.
Yeah. Fine. So I just mean if you're differential algebraists, I mean that it's universal over K.
But K is differentially closed also?
Yeah. Sure. That doesn't.
You want that?
If not, take the difference.
Why not?
So.
Okay.
Okay. So. Okay. Yeah. But if you're going to say universal in that case, then you'd better say saturated. If you're going to take any differential, if you're going to take any field extension, you better say saturated and not just universal to start. I think there's some issues there. Let's say.
Yes.
Okay. So. Okay. So now fix. So let's say that. So let's go back to V and let's say that V is in affine n space. And the dimension of V is D. Okay, so V is an affine n space. So now I want to fix a bar, a tuple of K independent differential transcendentals So I'm going to fix a tuple of differential transcendentals. That means that over K, A bar satisfies no differential polynomial equations, or equivalently, if you take A and all its derivatives, they're transcendental over K as an infinite set, as a countable set. Okay, so I fix a tuple of that nature, and what do I want the length of the tuple to be? I want the length of A bar to be n times d plus 1. Okay? And so now the map, I'll call it phi A bar, is going to be defined as follows.
Yes, it's very that's cool. Yeah, that's right.
To n. Sorry, I'm going on to the next line, but you'll see in a second what's going on.
Oh, okay. You need the generic forms, but you need one bit.
So
A little bit more than generic.
So yeah, more than generic.
Yeah.
So you might think that you could just sort of take a generic enough map like you do in Noether normalization or something.
Right.
I don't think so, because if you do, you may get some differential relations later on.
Right.
So you have to be careful about that. So this is more than just saying generic.
The second index means the derivative?
No derivatives. This is a map of algebraic varieties.
A as well.
A is a big tuple. It's of length n times d plus 1. And I index it by A sub ji, where the j ranges from 1 to d plus 1, and the I ranges from 1 to n. Okay.
Oh, so those are the coordinates of A.
Okay. And so, well, the claim is, and you can check this, that this map suffices.
delta neutralization.
Yeah. I mean, it's not so surprising that this map works because it's linear in the coordinates, and so as long as it's birational, it will preserve it. Okay. But what's essential for this? What's essential for that last statement that I said to make sense is that you had to start with something irreducible. I'm not claiming this works for tau L. In fact, I think it probably doesn't. Because if you try to do this for tau L, the reason I say I think that doesn't work is that for tau L, if you have a big codimension variety embedded in affine space, you should be able, for a bad enough singularity, to get the dimension of the tau L's to grow really, really fast, faster than would be possible for a hypersurface. So I think that you can't construct such a rational map for the jet spaces. I'm not sure why you'd want to. Okay, but I am sure why I would want to do this. And so now, let's just follow the line of reasoning now. If we can calculate B sub L of V1, if this is bounded by the degree of tau sub L of V1, then we have a degree preserving map. So we've accomplished our goal for an arbitrary V for B sub L, not for tau sub L. We know what this is quite explicitly. So what do we need in order to know this inequality? So, well, for that, we need to prove, so we need to show that B sub L of V, well, at least for a hypersurface, but you can do it in general, is a component of tau sub L.
Oh, because the degrees were sum of components, so you're kind of cheating here. Yeah. Okay.
So we'll be done if we can show that. Now, remember what I said about these important properties of the tau map. So tau sub L, tau, the functor, is, let's just remember, well-behaved on smooth varieties. Well-behaved on smooth varieties and well-behaved on smooth varieties and respects tall morphisms. We don't even need the full power of that. So,
Well behaved means that's equal to VL.
yeah, equal to BL. That's, for me, that means well-behaved. Okay. So using these two facts, so you can prove you really only, well, okay, you have to know something about the dimension of B, but really only these two facts. So if you take arbitrary V, take arbitrary V, and then look at the open map from the smooth locus of U to V. Well, what happens? It's exactly true that you know very well how to calculate tau L of a variety like this. And the map is really well behaved here. It's a tall. So it gives you everything in those fibers. Okay? So it follows.
Well, I think it's even an open. Tau L of U is an opening tau L of V. You don't need a tau. It preserves open immersion, I think. That's true in general. Yeah.
It might be true in general. I haven't shown them.
Yeah.
So I'm
What-
not.
Oh, okay. I'm always thinking without twist. I don't know.
Oh, okay. Yeah.
Yeah, sorry.
I think that's.
take my back.
I think that's true without the twist. I'm
Yeah.
not so. I'm not sure if it's true with the twist. Although I would suspect it would be. But
What was the question?
what
What was the question?
about whether it respects open immersions?
That's true.
You think it's true in general? Yeah, I think it probably is. I don't want to commit to it because I haven't
Yeah,
written proof of that.
I think.
Yeah, I think it is though. And so it follows that there is a unique component of tau L of V which surjects onto V. And this component has the right dimension. Has dimension dim V times L plus 1. Okay, so you could probably almost prove all of this with the classical jet space theory, like Hans is saying.
Yeah.
Well, you'd have to do it for twists, twisted things.
Twists don't really
Well,
do too much.
okay, but you have to prove something.
At least the dimension falls from differential algebra.
Yeah.
The dimension follows from differential algebra. Of
yeah.
course,
That's
the
the
And the
dimension.
uniqueness of that component.
Yes,
That's-
yes. The dimension follows from differential algebra, of course. Okay. So how does this picture look? So one of the reasons, okay, so I'm in general, so far I've really only been doing this for the ordinary case, right? So I've really been doing ordinary differential equations. How does this whole picture look in the partial case? Okay, so question. How does this picture look in the partial case? And the answer is that the picture on just the sort of geometric data that I'm talking about looks exactly the same. Okay? The setup is a little bit different. You have to set up the V restriction a little different. Of course, what are you looking at in the partial case? I mean, it's clear, okay, well, it's clear if you're a differential algebraist, but I mean, look, I said you're looking at the derivatives up to order L. I mean, so if you're a differential algebraist in the partial case, you're looking at what often people denote by capital theta of L. So this is the set of one to the alpha 1, the n to the alpha n. Omar, can you remind me, is it strict or not strict in our paper? The inequality. So it's the sum.
Doesn't are equal.
Less than or equal. Okay, good. The sum of the alpha i's, I equals 1 to n, is less than or equal to L. So you look at those as your differential operators. And then there's a remarkably similar picture given by the prolongation theory of Musa and Scanlon. So it's not true, of course, any longer that if you prolong the coordinates with respect to these, or you prolong the ideal with respect to these, that you get something that is that you get something that represents the k of t mod t to the L plus 1 points, but you do get something that you know represents the k of epsilon 1 through epsilon. Sorry, I want this to be m, just because I used n already, and for many things, and haven't. But you do get something that represents the
Should be outside.
oh, it should be outside.
Outside the
Yeah,
L plus
that's
1
right.
should be
Sorry, yeah, you're right.
Yeah, that's actually, I was curious about what's going to come.
What did I use? L plus 1. The L plus 1 power of that idea.
Ah, okay, this I think.
Okay, and so And there's some similar results connecting looking at the R of epsilon mod, that ideal points of a variety, that's a representable functor. Mustasa does that as well, but not quite as much. Yeah.
Does the Moses-Scanlon stuff work with commuting derivations?
Yes. Yeah. It works on the level of okay. So subpoint, not their model theory. Their general theory of prolongation spaces does. Not their right. So Musa and Scanlon do this in order to set up what are called geometric axioms for differentially closed fields. And what they do does not work in the community case, but their general geometric theory does. Yeah. Okay, so so far I've calculated the degree of a certain variety, and that's all. But that's really essential for what Omar and I want to do. And so, do I have maybe a few more minutes, or?
One theorist would like to run away in about 4 minutes.
Oh, right.
Okay,
5 minutes.
that's fine. So
We can run fast.
So I want to explain why I wanted to do this in terms of the problem that we set out to solve. Okay, so there's for this kind of problem, it seems really convenient not to work with differential polynomials, but to work in a slightly different category, and which is similar to what you might have heard called the category of D varieties. Okay, and I don't want to say exactly, all the formalism associated with that, and I'm not working exactly in the category of D varieties. So the idea is that you can encode. Let's see. So you can encode any differential algebraic variety. There's nothing deep about this. Okay, so by that I mean a zero set of some collection of differential polynomials as a pair of algebraic varieties V, comma, W, where W is a subvariety of B. You could do BL, but in general, by doing some variable substitution, you can make it B1 of that's always of that. Okay? And a lot of times I think it's nowadays it's one kind of misses out or misses why. Okay, so I mean, originally when these theories were axiomatized, the theory of differentially closed fields was axiomatized. Yeah.
When you say this encode, do you mean rational, birational, or differentially birational?
No. Well, in this formalism, I mean, you can literally get a bijection between the set of this. Okay, in this formalism, you can get a bijection between any differential algebraic variety and something that you write like this. Let me write that, and let me say what that means.
Yeah,
so
category.
VW sharp is the set of U bar in V such that U bar, delta of U bar, I'm only looking at the U points of this differential algebraic variety where U is a monster model, is in W. It's just a way of encoding it at this point. I'm not working in different categories. I'm just encoding something. You can set up a category of D varieties where oftentimes you'll take, instead of taking a variety here, you'll take a regular map to the tangent bundle or the twisted.
So right now
tangent
it's only
bundle.
set?
But right now this is just a bijection on the level of sets. And that's all I want. So model theorists tried to set up after things were originally axiomatized, okay, by various people for differentially closed fields, okay. I mean, And from some of the from some of the explanations of what a differentially closed field is, it's clear that it has first order axioms, and from some it's not. Okay, but various people had their different purposes for that. So I guess starting sometime in the mid '90s, there arose this notion of geometric axioms for DCF. I mean, at least this is what model theorists call them. Okay, so and what the geometric axioms would say is just information about what a priori looks like algebraic varieties, except for this map here, D. Okay? So it's a fact that if you take a differentially closed field, and you take... I'm sorry, why did I sharpen this on? There, that's better. Okay. If you take a differentially closed field and write things in this form, and if it's true that W projects dominantly onto V, then it's true that you can take any open subset of the base and find a point in the sharp set outside of that Zariski open subset. And so in particular, that means that you can tell when a solution set is infinite, of course. Okay? Because if you only had finitely many points, well, you definitely couldn't do that. So what is the procedure for figuring out what this finite set is? So the basic procedure is to use what I just said, which is what I'd call a geometric axiom for DCF 0, and to run an algorithm, which I'm going to informally describe only in the ordinary case. Okay? So the algorithm works like this. Okay, step 1. Okay, if the projection of W, V, is dense, output the degree of V equal, and that is the degree of the Zariski closure of the differential algebraic variety. Okay? If not, so if pi1 of W closure is proper in V, so that's a proper closed subset, I wrote that for Zariski closure, then replace V by pi1 of W closure and replace, I'll be done in 30 seconds, and replace W by B1 of pi1 of W closure intersect W. Okay? And now you have a new pair VW. Okay, so this is a new pair V1, W1. You can go back to the beginning and run this algorithm till it stops. The number of steps in the algorithm is of course bounded by the dimension of V because you're descending dimension at each point, and the degrees you keep track of by the arguments that I gave earlier and some basic intersection theory.
And you don't even have to assume that V is irreducible, I guess.
No, you can do it through choosing. Okay, so I think I'll stop there. Thank you.
Okay, I guess we'll resume in 15 minutes.
I think so, right? Well, I get 20.